now I want to talk about gravity. And once we start talking about gravity, we need to talk about forces. So gravity isn't just on Earth. Gravity can be defined for any two masses. And so in this case, you can think of these as being out in space. Maybe this is a planet and this is a star, right? So we call this Newton's law of universal gravitation, and we're going to look at the calculation that we would use for this, which would be, for instance, thinking about the force between the sun and the earth. Now, one thing that's important is that gravity is acting on both of these masses, that this planet is pulled towards the star and the star is pulled towards the planet. And so we're using the subscripts to represent that 2 on 1 and 1 on 2 have equal magnitude and opposite directions. In Chapter 7, we'll talk more about this, that this comes from Newton's third law, but right now you don't need to worry about that too much in detail. What you should recognize right now is that, again, we're saying that these two magnitudes are equal, and we have three variables that are going to appear a little bit later. We have the distance between their centers, and we have the masses of each of them. So again, if you think you know that gravity equals mg, we're talking about something different right now, and that's where it might be helpful to think of this as a planet and a star, though actually this is a force we can measure between two spheres just in the lab on the ground as well. So mathematically, there's this equation. I'm only using this as an explanatory aspect. We're not really going to be working with this in detail in this class, and this is again universal gravitation. And that just implies that it's different than what we usually talk about when we're on Earth. So again, we have those two masses showing up, and we have then the r, the distance between them squared, on the bottom. So now, this capital G is actually a constant, and this is called the universal gravitational constant. So that is always a constant with this value and these specific units. But now let's imagine that we're on Earth. We're thinking of M1 as being the Earth, right? So M1 is the Earth. So M2, now we're not going to think about this for the sun, we're just going to think about this as some random object, right? This could be a ball, this could be me, this could be a bird, whatever you want. We're just going to talk about some sort of object that's on Earth, and we're thinking about the magnitude of the gravitational force between whatever our object is and Earth. So the mass of the Earth is fixed. We can plug that in. The radius of the Earth is fixed, and the reason this goes in is that the distance we are from the center of the Earth is basically just the radius of the Earth. So we have that, and now we can plug those in and see that G is a constant, M Earth is a constant. Oops, that's a mistake. This should be R Earth squared. Sorry about that. And this is a constant. So if I wanted to, oh, I see what happened. My squared ended up in the wrong place. That's not there. This can become a new constant, right? That if what I have is some constants multiplied and divided by another, I can just group them together and make them a new constant. The mass of my object stays because that's a variable, and I get this new equation that's actually going to be how we calculate gravity on Earth. So the reason I'm going through this is, again, the force of gravity equals mg is something that people might be familiar with from a previous physics class, but what's important to understand is that it's actually a special case of universal gravitation where we've assumed that the Earth is one of the things involved. There's some object otherwise, and you track its mass here, and that we know what the distance is because we're standing on the surface of the Earth. Now again, if you're up in an airplane, even that change in distance is really small compared to the radius of the Earth, and that's why we don't worry about G changing even if you're, for instance, on an airplane. So one other approximation that I would like to point out that we're always making is that the Earth is basically flat. Now the Earth is not actually flat. However, in that first picture of universal gravitation, I showed two spheres, right? We think of the sun and we think of a circle. That's because it's a sphere. But once you're close to the surface, right, it looks flat. We don't realize that we're on a curved Earth. It just looks flat to us. The horizon looks flat even if we go up relatively high, like in an airplane, it still kind of just looks flat. So because of this, we just really worry about the radius, and we just say that the force of gravity is down. So this is something that's always kind of happening, and so that's one thing to remember, is that when we say the force of gravity is down, well, actually we mean towards the center of the Earth, but wherever you stand on the Earth, the center of the Earth is actually down. So there's nothing too tricky here other than pointing out that we're typically ignoring the curvature of the Earth that is really there, but it's okay. We don't need to worry about that. And once we are in the situation where the Earth seems flat, this distance here is so small compared to the radius that, again, we're not worrying about the change in gravitational force due to being a little bit above it. If you were far enough away from the Earth that the Earth looked like a circle, at that point, yes, you would want to actually consider a change in the gravitational force. Lastly, I would like to talk about gravity and Newton's second law. So the force of gravity, we said, is the mass of whatever object we're considering. I'm just keeping this subscript here to remind you that we're not talking about the mass of the Earth. The Earth is implied, it's actually in g. So the force of gravity is the mass of our object, like our ball, times g, which is a constant, and I'm obviously using g, which we've met before, as 9.8 meters per second squared. Now, this may or may not be surprising to you, depending on what physics you've studied before. And I've explicitly put the direction here as negative y hat, meaning down. So that's our gravitational force. Now, Newton's second law said that our net force is going to be equal to the mass of whatever object we're considering times its acceleration. And F net and acceleration are in the same direction, they're both vectors. So let's consider an object in free fall. And the whole point of free fall is that the only force acting on it is gravity. So that means that F net is equal to Fg, and I can actually draw that over here, right? This is my F net, because I only have one force. Nice and simple. So what that means is that if I have an object in free fall, these two are equal. So what does that actually tell us about our acceleration? Well, our acceleration due to gravity, i.e. from there, is going to become the mass of my object times g, which is coming from this. And here I'm talking about magnitude. I'm not explicitly worrying about direction. And I divide it by the object. So this was here. And I'm dividing it by the object because of Newton's second law. And obviously, my object is going to divide out the mass of my object, and I'm left with g. And if we worry about the direction, we would say that if this is a vector, this is going to be in the negative y hat direction. So again, this isn't necessarily surprising, but what we've shown is that the gravitational force does depend on the mass of your object. But when you consider Newton's second law, the mass of the object divides out such that the acceleration is constant. So the main takeaway here is that the acceleration due to gravity, which we've met and just called g, is constant. And again, this is chapter 2 material that you're hopefully comfortable with now. But the force of gravity actually, just magnitude, is mass times gravity. This depends on mass. And the reason that's okay is because of Newton's second law, saying that mass is also the relationship between acceleration and force. So there you go, that's the idea. And again, the big takeaway here is understanding why acceleration is constant, force is not.